Hi and welcome to lesson 3 of the Esters, Fats and Oils topic. A starter question to start you off with. This is quite tricky, but we went over this in the last video, so hopefully you are able to use that and your notes to have a wee go at this. It's write an equation showing how propanoic acid can be produced from the ester butyl propanoate. See how you got on with that. So lesson 3, we are going to be looking at fats and oils. Now this is the kind of last part of this topic, this subsection of the topic, and our learning intention is to explore the structures of fats and oils as well as their properties and how they can be produced. We want to be able to describe the structures of both fats and oils because these differ slightly, as well as their properties, and write equations for the formation of triglycerides, which are fats and oils. More about that in a wee second. So, fats and oils then. Now, this video is going to contain quite a lot of information. There are lots of blanks, tables and things to fill in your notes, so make sure that you are listening carefully and writing down all of the things in your notes that you need to fill them out. So fats and oils are essential to the human diet because they provide two things: a concentrated source of energy, more concentrated than you get from, for example, carbohydrates, and also transport and storage of fat-soluble vitamins. If you do not have fats and oils in your diet, then you're going to have no way for fat-soluble vitamins to move around your body. Some of the fat-soluble vitamins are vitamin A, vitamin E, vitamin K, C and B are the water-soluble ones. Fats and oils, as we know, are insoluble in water because they are non-polar molecules. Like dissolves like, water is polar, so fats and oils, non-polar molecules, are not going to dissolve in water. So fats and oils structure. Fats and oils are an example of some esters formed by a condensation reaction between an alcohol, which in this case is glycerol, and this is glycerol here, and carboxylic acids known as fatty acids. Now these are just carboxylic acids with very, very long carbon chains. So it's exactly the same as an ester reaction. So esterification is a condensation reaction, but this time we have a compound called glycerol. So the alcohol is this thing here called glycerol. Now, as you can see from the diagram, glycerol is a triol, so it contains 3 hydroxyl groups. There's 1, 2 and 3. Its systematic name, if we had to go about naming this, is propane 1,2,3 triol. Now remember your dashes and commas here to make your naming accurate. So fats and oils contain glycerol combined with fatty acids in the ratio of 1:3. So if you have 3 alcohol groups, how many acid groups do you need? You're going to need 3. So for every 1 glycerol molecule, you're going to need 3 fatty acids. And just like esterification, we're going to lose the hydrogen from the alcohol, lose the OH from the carboxylic acids, or fatty acids in this case, and that is going to form our ester link, just as before. All of these things, though, about glycerol are important knowledge that you can be asked about in the exam. So it's a condensation reaction. You need to be able to draw glycerol, and you need to know that its systematic name is propane 1,2,3 triol. You also have to be very aware of the 1:3 ratio, but of course that should make sense once you have seen the process of this reaction. So let's have a look at that. So the structure of glycerol then is, as we've seen on the last page, propane 1,2,3 triol. The carboxylic acids which attach to the glycerol are just referred to as fatty acids. They are many are straight chain carboxylic acids, but they can be saturated or unsaturated. To find that out, you would have to look at the number of carbon to hydrogen ratios and see, is it CnH2n plus 1 or is it CnH2n? Use your kind of alkenes knowledge for that. The reaction between glycerol and 3 fatty acids is, like we said, a condensation reaction, so it's going to produce some water molecules, which produces a structure known as a triglyceride. So you have your 1 glycerol reacting with your 3 fatty acids. Now the fatty acids don't have to be the same, they can be different, but it's going to produce this structure known as a triglyceride. Now your triglyceride is just your fat or your oil, so it's this structure here. Now what we've done here is we've taken glycerol and we've added 3 of the same fatty acid, and we've labelled the carbon chain just with a blue R. Now that R can stand for anything. It could be 1 carbon chain, 2 carbon chain, a 20 carbon chain. It doesn't matter. The important part is that we know how to take the OH from here off, the hydrogens from the alcohol groups, the hydroxyl groups off, and join up the structures to create this triglyceride, which becomes our fat or oil. It's very important that whatever the R chains are, you write them down exactly as you see them. And we also obtain 3 water molecules because there's 3 hydroxyl groups, 3 carboxyl groups, so we end up with 3 water molecules as a byproduct. Now, just like before, our C double bond O are our ester links, and these are found in our triglyceride or our fat or oil. That is quite a lot of information. That is quite a big equation to look at. You are going to be copying this into your jotter, or you have a picture of it already in your jotter, in your notes booklet. Make sure that you have a really good look at that. We will practice drawing these as well in class so that you know exactly where each part comes from. So, properties of fats and oils. Then now that we know how they're actually made, what are their properties? Well, first of all, oils have a lower melting point than fats. Everybody knows that already because fats like butter, lard are usually solids, and olive oil, vegetable oil, etc. are liquids at room temperature. Why is this? Well, there's a very specific reason for this, and it's a very common exam question as well. Fat molecules are saturated. So remember, saturated means that the molecule contains no double bonds. So that means that the chains are able to pack together really, really closely. So in this diagram here at the bottom, this one here, you can see that the chains are able to pack together. They kind of look like tuning forks, the way they line up together. But they're able to be together very, very closely, almost like bricks in a wall. They're all packed together. Oils, on the other hand, cannot pack together like this. Oils are unsaturated, which means they contain double bonds. They might not just contain 1 double bond, they contain 2, 3, 4. Remember, the chains are very, very long. So the double bonds make the chains distorted, and by that we mean they don't go in a nice straight line. They can go off at different angles. That makes it very, very difficult for the molecules to pack neatly together. And what this does is it affects the intermolecular forces. Here is a little summary of what we've talked about so far. This again is a little kind of fat versus oil summary that you can copy down into your notebook. Where the LDFs are concerned, though, this is a very, very important question. It comes up all the time in exams, and you need to know a really solid answer for it. So why are fats solid at room temperature but oils are liquids? So you have to mention that fats are saturated and oils are unsaturated. The efficient packing of fat molecules allows the intermolecular forces of attraction, which we know are LDFs, because we are working with non-polar molecules here. LDFs are going to be the strongest intermolecular force of attraction. So if the molecules in fats can pack closer together, that means that the London dispersion forces are strong enough to hold the structure together. They're close together because it's able to pack together, and that means that they are strong at room temperature and can hold the molecules together in a solid structure. Oils, on the other hand, the chains are all distorted, which means that the molecules are further away from each other. The London dispersion forces, this means, are much weaker, so less energy is required to overcome these. So the melting points of oils are below room temperature, which means they are already melted. They are already liquids at room temperature because of that reason. So this is very, very important. It gets asked a lot. Make sure that you understand why fats are solid at room temperature, but oils are liquids. Another common exam question, or it sometimes comes up, not as often as the first one, but sometimes, is the degree of unsaturation. Now this is usually a problem-solving question, but I'm going to give you some pointers here. So double bonds in the fatty acid chains are the thing that prevents an oil molecule from packing closely together. So the greater the number of double bonds, the weaker the London dispersion forces present. So that means that the more double bonds there are, the weaker the London dispersion forces, the more unsaturated it is, therefore the lower the melting point. So what you can do is you can test the degree of unsaturation in a molecule by adding some bromine water. So what you would do is you would shake your oil with some bromine water. You might have to dissolve it in some hexane or something first so that it dissolves and you can mix it with bromine water. But the bromine, as we know from that 5, if it comes into contact with something that is unsaturated, then it rapidly decolorizes. So the more bromine you can add to your compound in your test tube, the higher the degree of unsaturation. In other words, the more double bonds there are. The higher volume of bromine water required, the higher the degree of unsaturation. So that can be a good way to test how unsaturated an oil might be. If you wanted to make it really, really accurate, you could use a burette or count the number of drops with a dropper if you're working with small amounts. That would maybe be something that could come up in an open-ended question. If you're talking about the properties of fats and oils, definitely add in a bit about the degree of unsaturation and how you can test for that. Okay, hardening of oils then. So just as it sounds, this is a process that we use to convert the oils into fats. So what we're doing is we're taking something that is unsaturated, so our oils are unsaturated, and we add hydrogen across the double bond. So we've done this before in Nat 5. This is an addition reaction, and because we're adding hydrogen, it's called hydrogenation. Now, a nickel catalyst is used. It's important that you know that it's a nickel catalyst that's used, and we end up with something that is then saturated. So oils can be converted to fats through hydrogenation, and of course uses a nickel catalyst. This is actually the process by which margarine is made. So margarine starts off with, I think it's plant oils, and it's then hydrogenated using a nickel catalyst and becomes solid margarine rather than liquid oil. So we have some questions here. I'm going to let you pause the video, and then when you play it again, we will go through the answers. So the answers to the questions then. Number 4 is name and draw the functional group present in fats and oils. So fats and oils have the ester links present, which is C double bond O, O. 5 is name the reaction which produces fats and oils. It is a condensation reaction between glycerol and fatty acids in the ratio of 1:3. 6, in what ways does the structure of a fat differ from an oil? Fats are saturated, whereas oils are unsaturated. Now, number 7 is a 3-mark question, which means we're going to need 3 points for full marks. Fats and oils have similar structures, however, oils tend to be liquid at room temperature, whereas fats are solid. In terms of the structure of fats and oils and the intermolecular forces involved, explain why this is the case. Well, fats can pack closely together due to them being saturated. Oils cannot pack closely together due to unsaturated molecules with distorted chains. The LDFs between fat molecules are therefore stronger and more energy is required to break these than oils, and that's why oils are liquid at room temperature and fats are solid. So all three of those points have to be mentioned for you to gain all of the marks. Last one, olive oil can be hardened during an industrial process. Name the catalyst, it's a nickel catalyst. And B, explain what is added to the oils to produce fats. So hydrogen is added across the double bond to produce the fats. Hopefully we were able to answer all of those questions correctly. Remember and upload evidence of your answered questions onto the Google Classroom. So we wanted to be able to describe the structures of fats and oils and their properties, as well as writing equations for the formation of triglycerides. Writing the equations we're going to practice more in class because that's quite tricky, but we should have a really good understanding of the structures of fats and oils and their properties as well. So in other words, why are fats solid at room temperature and oils are liquids? That is the end of lesson 3, fats and oils. Thank you for watching.